Hello. I welcome you all to this another interesting screencast. And the problem reads: draw the axial force diagram, shear force diagram, and bending moment diagram. Assume that CD, which is this connected cantilever beam to the column, is located 1 meter from B. All right. So this is a modified problem that we already did, problem 7.5. If you remember, I posted this video. You can check on how we found the actual problem itself. We are being asked to find the internal forces at A, which were the axial force, shear force, and bending at A and B, and we calculated that. So we are not going to go through all the steps that we did in the previous video, and moreover, I'm going to show you a summary of the solutions that we found in our previous video on this particular problem. The purpose of this particular video is only to explain and later on draw the axial force diagram, shear force diagram, and the bending moment diagram for this structure where we have a column connected to a beam or a beam connected to the column. Okay, I hope this is fine. So if you remember, let me show you what we did in our previous video. This is what we did in our previous video, remember, right? We have been asked to determine the internal force, the shear force, and moments at point A and B in the column. And we did that. So we are going to use these values that we found in this previous video so that we have the forces, especially the internal forces at B, as well as this column. This column, we are going to section it so that we separate it, all right, because it's going to introduce an axial force as well as a moment in the column, all right, at the connection here through the neutral axis. All right, so there we go. So what are those forces? Let's include them. So here we had this force, an equivalent force of the component of this. Remember, this had two components, right? Remember, it had two components. It had this component. This component was 6 cos 30 degrees, and this component was 6 sine 30. All right. So 8 was adding plus 6 cos 30. Remember? Okay. And what did we get? We had 8 plus 6 cos 30. And the total value that we got from the previous video was 13.1962. Okay, and then we had this other force here, this horizontal, which is just equal to 3. Okay, because sine 30 is 0.5, so this one was a 3. And we also had the moment here. We had the moment. Okay, we had the moment that we calculated about E, which is a point along along the neutral axis. Neutral axis is an axis where the longitudinal stresses as well as strains are equal to 0. Okay, so we had this moment because these loads are eccentrically loaded, and therefore they are going to cause a moment about the neutral axis. All right, and what was that particular moment? All right, so we had to say 6 cos 30 by 0.4. Okay, this one is causing clockwise, right? And then 8 by 0.4 causing anti-clockwise, and then we sum them up together. All right. All right, let's do it. So we had the moment. This moment was equal to 6 cos minus, okay, like we said, this is causing anti-clockwise. So we said 6 minus 6 cos 30 by the lever arm 0.4, and then plus 8 by 0.4. And then when we summed up this, let's work it out. Minus 6 cos 30 times 0.4 plus 8 by 0.4. All right, we had a moment of 1.1215. Remember, right? 1.1215 kilonewtons meter, and it was a clockwise, anti-clockwise moment. Okay, So that is how we found those values. Okay. And then we're also interested in finding values at this point at B. So we also did a section here. We did a section, and then use the top. We use the top section, okay, because this is where the loads are coming from. The loads are coming from wherever to the column, and then they are being transferred from up down. All right. So even here, we also found the reaction forces. We had the moment in this direction, and we also had the moment in that direction. Let me start with the shear force. We had the shear force in this direction. Okay, we had an axial force in this direction, and then we had the moment in this direction. Okay, all right. And for this particular beam where we have this applied force here, which is a 3 kilonewtons. Therefore, we expect to have a shear force at the very end here, okay, which also is just going to be equal to 3 kilonewtons. And then we expect to have, because this is going to cause a moment in this direction, which is anti-clockwise, therefore a moment that will counter that will be anti-clockwise, and this moment is just equal to this. All this stuff that I'm explaining, I explained it in the previous video. This whole length here for this particular beam was already given. It is this length here. This length here is 1.5. Okay, 1.5 meters. All right, and therefore this moment here will just be 3 by 1.5, which is a 4.5 kilonewton meters. All right, kilonewton meters. The only thing that we introduced ourselves was just assuming the length of this column from B, okay, because we need that for us to draw at least these diagrams from B to A, including that beam or cantilever beam. Okay, so if we have these particular components here, what do you think? For them to equilibrate at a point where they are connected, because this is all continuous, we don't have any hinge. All right, so if it's continuous and it's connected at every point, we expect a transfer of moment, transfer of forces in the x direction, transfer of forces in the y direction. Okay, so we also expect another component here. Let me put it in red, of similar magnitude that will equilibrate. So we are going to have this component here, which is going to be a 3 kilonewtons, and we'll have moment also here in the opposite direction like this, right? You agree, right? In the opposite direction. Okay, we're going to have a moment, and this moment will have magnitude 4.5 kilonewtons meters. Okay, these are there for purpose of equilibrium. All right, and then later on we are supposed to find this moment. Remember this moment, to find this moment, this V and this N. Okay, and if you remember, V, we calculated it as just equal to 3. Okay, of course in our case we had assumed this V to be in this direction, therefore we had indicated a minus to just show there was supposed to be change of sign, right? And then M also, if we are to calculate M, we say summation of moments about point B, we are going to have a minus M there. Okay, then we'll have a plus 4.5. Okay, then we are going to have this whole length here, it is 2.9, right? So we have 4.5, and then we are going to have plus 1, 1, 2, 1, 5. Then later on we'll have another plus, which is 3 by 2.9 equal to 0. Therefore our M is supposed to be equal to 4.5 plus 1.1215 plus 3 times 2.9. Okay, so we found this M to be equal to 14.3215. Okay, And then this n also, if we are to sum up forces in the y direction, we'll have n minus 13.1962 minus 3, okay, then equal to 0. Okay, therefore n is just going to be equal to, so we have minus 13.1962. all right, and then we have a minus 3, and then we have n equal to 16.1962. And then the way we found our v, we had summation of forces in the x direction. So if we do so, we'll have a v minus 3 equal to 0. Therefore, v is just going to be equal to 0. All this stuff we did, I'm just repeating it here. Okay, so let's replace these values. So there we said our n is equal to 16.1962 kilonewtons, and then we have that shear force, which is just equal to 3 kilonewtons, and then we have m, which is our moment, which is just equal to 14.3215, right? Okay, 3215. Great. So let's get rid of this so that we move on. Yeah, so this is kilonewtons meters. All right, so once we have this information, then we are great to go. Okay, we are good to go. Okay, so then let's draw the shear force and axial force diagram. Let's draw shear force and axial force diagram, as well as bending moment diagram. Again, we are using the differential equation. We have the change of the axial force with respect to x is equal to the axial distributed force, which is just our q. We can call it q. And then axial force itself will just be equal to the area under the axial distributed force. And then the change of shear with respect to x, the rate of change of shear with respect to x is equal to the distributed force, which is applied perpendicular to the longitudinal axis of the member. All right, and then our shear force is just going to be equal to the area under that distributed force. And then we have the rate of change of moment with respect to x is just equal to the shear force, and moment is equal to the area under the shear force diagram. So we are using these three equations to just make a drawing here. All right, so let's start with the shear force. Like I said, the main purpose of this video is to just draw these diagrams, right? So at B, what do we have at B? At B we have and we also know that I just make mention of something. We also know that when a member is under compression, so a member is under these forces, we normally denote it as negative. Okay, this is negative. And when a member is under tension, we normally denote it as positive. Okay, so we are going to use the same notation. All right. So I've already indicated here plus and minus of this member. We are going to be moving from B going towards E for the column, and then for the beam we have positive up, negative down. Then we're going to be moving from C to D like I've indicated these arrows. You've seen, right? Great. All right, let's get moving. So at B we have an axial force of how much? 16.1962. So let's say our negative value, that is so thick, let's change it up to, let's say, somewhere there. Okay, let's say that value is our that's a value at B, the initial value boundary value, which is a 16.962 kilonewtons. Okay, so let's say that is the initial value there, and then Let me move this just a little bit. It's too long. Of course, you don't need to maintain 4 decimal places when you are working. This is just for me to just maintain accuracy. The final answer, 2 decimal places are enough. Okay. So 16.1962, again, it's dependent with what your professor wants you to find. Okay. So we have an initial value of 16.1962, which is a negative in the sense that it's undergoing compression. And then from B to E, we don't have any axial distributed forces equal to 0. Therefore, our rate of change of the axial force itself is also just going to be equal to 0, or its slope is equal to 0. Okay, right. So we expect the slope to just be equal to 0, and it will be a straight line. Okay, it will be a straight line. So from this point, this is just going to be a straight line. Let's use the color of my choice, which is green. So from here, it's just going to be 0. But when we reach D, okay, when we reach D, what happens? D, we have another component in the opposite direction, all right, which is 3 newtons, okay? So what happens? The two are going to interact. The two are going to interact. So we are going to have a 16, which is negative 16, because this is a direction that we chose as our negative, which is going up, all right? So anything that is going to be in the opposite direction that we've chosen is going to have a different sign. So 16 minus 16.1962 plus 3, what does this give us? It gives us a 13, right? It gives us a minus 13.1962. All right. So this will be reduced. Okay, this will be reduced. It will go in. It's going to go in like so. Okay, then it will reach this value, which is 13 point something. Okay, let me indicate it. So this is 13. Let me indicate this value. We are saying this is 13.1962 kilonewtons. All right, this point here, okay. So from that point onwards, we know again to say our Q from this one was from from B to D. This one was from B to D, and then from D to E, we know that our Q again is equal to 0. The axial distributed force. Don't get confused. Okay, this is 0 there for the slope. A prime or dA dx is also going to be equal to 0, the slope of our diagram. So this is just going to be a straight line. A prime is just another notation that we can use for derivatives. So A prime is just equal to dA dx. Okay, right. So from that point, we expect a 0 slope, which will just be a straight line to that point like so. And then when it reaches E, the two are going to interact. What we have there at E, we have another value which is going in the opposite direction. So you know what happens, they'll add up algebraically. So we have a minus 13.1962 plus a 13.1962, which gives us a what? A 0. Therefore, a what? A closure. Right. So let's close this. I prefer my color. Let's close this. There we go. Great. This closed. So the whole lot of this is negative. Our beam is undergoing compression from B to D. Only that the compression is higher from B to E. The compression is higher from B to D, and then it reduces later on from D to E. So this is how it is distributed. This value here is 16. Great. This one is a 13, which is the same here. This is a 13.1962 kilonewtons. Great. This is all negative. All right. Okay, so now we are done with the shear force diagram. The axial force diagram. We are done with the axial force diagram. Sorry. So now let's move on to the shear force diagram. Let's move on to the shear force diagram at B. What do we have at B? At B, again, the initial value for shear at B is negative, like we said. This direction is positive, this is negative, this is positive, this is negative. Great. So at B, we have a negative initial value of 3. Let's say 3 goes up to there. We don't have so much space. 3 goes up to there, okay? And then let's write down this value here. This is a 3 kilonewtons. This is a 3 kilo newtons, okay? It's our initial value. And then from B to D, from D to D, okay? So this point is B, this point is D. We have an N, then we have E. The same applies to that. Okay, let me just write them down in advance. So this is D and then this is B. All right, so there we go. So let's now check what we have from B to D. In fact, here is just a whole lot of it. Is there's nothing. It is just at B and E. So from B to E, Q is equal to Q is equal to Q is equal to 0. This Q, please don't confuse it with the Q, the axial distributed force. This Q is the distributed force perpendicular to the longitudinal, distributed force perpendicular to this. Okay, this is the one we are talking about. Okay, this is 0. We don't have anything. All right. The one for axial, the one that we are talking about for axial, it will be going in this direction like this. Okay. All right. Okay. I hope I made this clear. Great. So the Q is equal to 0 from B to E, and therefore V prime, which is dV dx, is also just going to be equal to 0. This is the slope of our diagram. So we just expect just a straight line from one end up to the end, like so. Okay, and when we reach that end there, the two are going to interact. Which two? The value at E, so we have a -3, and then a +3, which is going to be equal to 0. So this will enable us to do what? To have our diagram closed. Great. So there we are. So this, the whole lot of this is negative. This value here is also 3 kilonewtons. So we are done with the shear force diagram for BD, okay, but we need also to draw for CD, okay. I forgot to mention to say we don't have any axial force along CD, so in there it's just going to be 0. I should have also drawn a line like so to just indicate that it is 0, like so, up to there. Okay, great. So then from CD we do have some shear force. The initial value at C, we have a 3. Okay, let's say 3 goes up to there. Okay, we have a 3 which is negative. Okay, let's write it down. We have a 3 kilonewtons, and then later on from C to D, Q is equal to 0. Again, this Q is perpendicular to the axis of the beam. We see this is 0. We don't have anything there, and because it's equal to 0, therefore we expect the slope for our shear to also be equal to 0. So this is just going to move up to there and close. And then when it reaches this point there, we have 3 kilonewtons, which is positive, and the two are going to interact. So this will close going up like so. Okay. So closure is very vital. Okay, and this is negative. All right, this is negative. All right, let's go to now moment. Let's draw the diagram for moment. Let's start with a column at B. What is our moment at B? At B, we have a clockwise value, of 14.3215. So we need to use a counter direction, which is counterclockwise, okay? Because if we are to make a very small section here, our internal moment is just going to be in the opposite direction, which is anti-clockwise of the same magnitude. All right. So that's the value that we are going to use there as our initial value. Therefore, we expect our moment to have this value of negative 14.32. Okay, so we'll have a negative value up to maybe somewhere there. All right, so let's write down this value. Let's say this value is maybe it's too high. Let's bring it up to here, just up to here. Let's say this value is we already know the value is 14.3215 kilonewtons meter. Okay, that's the value there. Okay, that's the value here. That's our initial value. And then from this onwards, let's look at what we have. Do we have anything? Of course we do. Let's start now working segment to segment. So from B to D, our V for our V from B to D is equal to is negative and it is constant, and therefore M prime also will be negative and constant, right? And then we need to calculate the magnitude of this moment, which is just V integral V dx, and we can compute there. We can compute it to just be minus 3 times 1. Okay, from B to D that length is 1, which just gives us minus 3. All right, so what is the final destination point? Then they will need the two interact. So we'll have a 14.3215 positive minus 3. When this subtract, we'll have 11.3215. Okay, 3215. So we'll have this final destination to D from here, and it will be a linear. It will be linearly varying. It will be a linear. It's a polynomial of degree 1, right? Because since our slope is constant, a polynomial of degree 0, we expect the function for moment to be a polynomial of degree 1. So let's say it is going to go up to maybe somewhere there like so. All right, and this value here, we say this 11.3215. Okay, 3215. All right, so let me move it a little bit, because I'll need to draw a line somewhere there. I'll need to draw a line and move it maybe up to somewhere there. Okay, and then at D, we have this moment that was introduced by the cantilever beam. Remember, there was this moment of 4.5. It normally causes discontinuity of our diagram. So when we reach D, the two again will interact. So we'll have a positive. So if this is anti-clockwise, so we are going to use a clockwise one. Remember, every time you have a couple along the beam or reaction force, which is a moment, we always use the opposite direction. Okay, and we've been doing so every time. It's important. It's a principle of an internal moment, okay, which will have an opposite direction. All right, so 11.3215. okay, so opposite of positive is negative, therefore it will subtract, so minus 4.5. so this gives us, so 11.3215 minus 4.5, it gives us a 6.8215. okay, so this is going to move like so. It will move from there up to a certain value. Okay, a certain value we are calling 6 point, this value here. Okay, so this value we are saying is equal to 6.8215. okay, is that clear? I think so. 6.8215. 8215. Great. And then from there onwards, then we'll now be heading towards, let's check the behavior from D2. Let's check the behavior from D to E. Okay, D to E. All right, what do we have from D to E? Our shear is negative, of course, and constant. Okay, and then we expect moment prime to also be negative and constant. And this magnitude moment is going to be equal to integral v dx, which is just equal to the length from D to E is 1.9, then times the magnitude of our shear, which is just a -3. So if we are to work out that, we have 1.9 times 3. So this gives us a 5.7. So the two interact. So we have a 6.8215 minus, this is minus, okay, minus 5.7. What does this give us? So 6.8215 minus 5.7, it gives us a 1.1215. Okay, so from here, and again you see a linear function, all right, because our shear is constant, therefore moment will be linear, okay, or a polynomial of degree 1. So from here we expect this our moment reducing in this order like this linearly, okay, up to E. Okay, and then we said this final value here at E, this final value, I know my diagrams are small because I lacked a little bit of space. This value here we said is equal to this value here is equal to 1.1215, okay, kilonewtons meter. Then when we reach at E we have a positive 1.125 or 1.415. At E we have a moment that is which is positive, therefore we are going to use an internal moment which is negative, right? So minus 1.1215, which gives us a 0. All right, so this is therefore going to close at this point like so. Okay, let me use green again, sorry. This is going to close like so. Great. Not good enough. This is going to close, okay, like so. All right, so this moment here is positive, this is all positive, it's positive. All right, and then let's look at now the moment from C to D. From C to D, from C to D, let's draw that. What do we have from C to D? From C to D, we have an initial. Do we have any initial value? Okay, from C to D, we don't have any initial value. From C, we don't have any initial value. And let's look at the shear. Okay, so we know that our shear is negative and constant. Therefore, you expect m prime, which is the mdx, to also be negative and constant. And this magnitude for m is just the area under the shear diagram. In our case, is equal to just -3 by 1.5. This is going to be equal to -4.5. Okay, 4.5. And we said its slope is negative and constant. Let me use a different color here. So negative and constant, we just expect a straight line, right? So from here, it will just be, oh no, it will just be a straight line, right? So it will just be a straight line, okay? Let's say it goes up to somewhere there. Okay, let me move that a little bit so that I don't disturb what I just wrote inside. I just move this a little bit. Okay, so let's say I use blue. It's linear, and linear is negative and this slope is constant, right? Straight line. So it's just going to be a straight line. Let's say it's up to somewhere there. Okay, and this value here course, when it reaches G, there's going to be a closure. Okay, so we have this 4.5. Then because the moment there is clockwise, but we are going to use the internal force, which is positive, which is anti-clockwise, so we are going to have a closure like so. Okay, all right. Let me get in straight lines. What is happening? Okay, from there, all right, it's not closing so well, sorry about that. All right, something like that. And then that value there, this value here is a 4 point, this value here is a 4.5 kilonewton meters. Okay, I think this is about it. This is about it. And this moment is negative. This moment is negative. Okay, so this is about it. We have drawn the shear force, the axial force, the shear force, and the bending moment diagrams for this particular segment of a column as well as a beam. And I hope the videos are helpful. And if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. For now, bye bye, and see you in my next screencast.